In this module we will talk about electric potential energy, work done by charges, and electric potential. When objects move they produce kinetic energy, and when they are at rest they have potential energy. Work can be expressed in terms of the change in kinetic energy or the change in potential energy. When kinetic energy increases, the potential energy decreases. Here we have an object with mass m and it falls from rest from a height d. The mass is acted by the gravity, hence the force of gravity F. Initially it has potential energy at position A. At its final position B it has kinetic energy. We also note that as the moves from point A to point B its velocity increases. Here the potential energy decreases and the kinetic energy increases as it moves from position A to position B. The work done on the mass when it moves from position A to position B is positive. Work can also be expressed as a function of the force and displacement. Since the mass is falling from a height d, the direction of displacement is also going downwards. Here we see that work is positive. We note that work is path independent. This means that the initial and final position is the only condition that matters. The work done by different paths will be equal regardless of the distance it travels, since it only needs the initial and final position of the mass. Similarly, the work done for electrical charges has the same property. Electric potential is the amount of work needed to move a charge against an electric field. As shown in the figure, we have a positive charge Q between plates. The charge moves in an electric field and the force here is the electric force that is exerted on the charge. The charged particle moves in the same direction as the electric force F. The work equation follows the same concept as that of mechanics, where we recall equation 2. Here the force F is the electric force, which is a function of the test charge and the electric field it is immersed in. In this scenario the force exerted by plate A to the test charge is repulsive, since both are positive. So we can write equation 2 as a function of the electric force, and we see that the angle between the electric force and the displacement as it moves from the positive plate to the negative plate is 0 degrees. So we have the work done on the test charge as shown in equation 5, and it is a positive work. As mentioned earlier, the work done on an electric charge is also path independent, so as it travels any path A, B and C it will produce the same amount of work, since it only needs the initial and final position. Here we look into the physical quantity of electric potential energy. So we recall the work equation as an expression of change in kinetic energies, or the negative change of potential energy shown in equation 1. As the charge particle moves from plate A to plate B it accelerates, so its change in kinetic energy increases. Inversely, as it goes from a high position to a lower position Y its change in potential energy decreases. So the work done in moving the charge is also shown here as positive using energy equations. But what do we mean by kinetic energy and potential energy for electric charges? For charge particles the kinetic energy is given by equation 6, which is just an expression of the mass of charged particles times the square of the speed of the particle. The potential energy is an expression of the charge and electric field, not as a function of gravitational effects. This is what we call the electric potential energy. Gravitational effects are ignored, since for such tiny particles its effects are negligible. The work function can then be written in terms of its electrical potential energy as shown here in equation 8. Let us examine different cases for charges moving between plates. As it accelerates towards the negative plate, its height is reduced, thus decreasing its electric potential energy. So the change in electric potential energy is negative, then work done using equation 9 is positive. If we solve this using its kinetic energy will also result in positive work. Here the work done in moving the charge is solved using the force and displacement function of work as shown in equation 2. Since the displacement and force goes in the same direction, then the angle between them is 0 degrees. This results in a work done that is positive. Here we have a charge moving in the opposite direction as the electric field moving from point B to point A, or it is moving towards the positive plate A. The change in potential energy increases since the difference of height gives the change in potential energy greater than 0 or gives a positive value. So its work will be negative as it moves opposite the direction of the electric force. Let us look at the work done using force and displacement for the systems earlier. Work done using force and displacement, we use the equation 2. Since the displacement and force goes in the opposite direction, then the angle between them is 180 degrees. This results in a work done that is negative. Here we use a negative test charge moving towards the negative test plate B. We see that the potential energy increases as it moves opposite as the electric force, or moving towards the negative plate B. The increase in its electrical potential energy as its distance becomes less is because it becomes less negative. The work done will result in a negative value since the difference of the potential energy gives a positive value. Here we solve work using the force and displacement vectors. Using equation 2 we see that the displacement and force goes in the opposing direction, thus the angle between them is 180 degrees. This will result in a negative value. So the work done in moving a negative charge from a positive plate towards a negative plate is negative. Here the negative test charge is moving towards the positive test plate A. We see that the potential energy decreases as it moves towards the negative plate A. The decrease in potential energy is because it becomes more negative. Calculating the work done and taking into account the negative value of the change in electric potential energy will result in a positive value of work. Here we solve work using the force and displacement vectors. Using equation 2 we see that the displacement and force goes in the same direction, thus the angle between them is 0 degrees. This will result in a positive value. So the work done in moving a negative charge from a negative plate towards a positive plate is positive. Based on the behavior of either positive test charge or negative test charge, we come up with a general rule for the electric potential energy. So the first is that the electric potential energy increases if the test charge moves opposite to the electric force and the work is negative. The electric potential energy decreases if the test charge moves in the same direction as the electric force and the work is positive. Sample problem. A 50 microcoulomb point charge moves from point A to point B shown in the figure below. The magnitude of the electric field at 2 times 10 to the power of 6 Newton per coulomb. Points A and point B are 80 centimeters and 20 centimeters above the negatively charged plate, respectively. Letter A. Calculate the electric potential at points A and B. Letter B. How much work is done to move the charge from point A to point B? For letter A. To calculate the electric potential at points A and B we use equation 7. So the electric potential energy at point A is 80 joules. Similarly, to solve for the electric potential energy at point B is 20 joules. Letter B. To determine the work is done to move the charge from point A to point B, we use equation 8. So we see the work done is positive 60 joules. We note that the change in electric potential energy is negative, thus it is decreasing and being converted to kinetic energy. Since there is a decrease in electric potential energy, then the kinetic energy is increasing. This suggests that the charge particle is increasing. So here we equate both equations for work and examine if it is consistent. So the expressions for work are given as the change in kinetic energy or the negative of potential energy. The other one is the work of force and displacement. The force here is electric force, which is the function of the electric field and the test charge going the direction d hat. And the displacement vector, which is the difference of the heights y and going in the direction d hat. Plugging in these equations we have the function here, and since both the force and displacement are going in the same direction, then the angle between them is 0. The cosine of 0 will result in 1 and we arrive at equation 11. So we see that the potential energies at point are shown here by equation 11, and they are functions of the test charge, the electric field, and the height y. The general expression for electric potential energy at any height h is given by equation 7. We now consider the behavior between 2 point charges. In this case we have two same point charges in space where you have a stationary point charge radiating an electric field. Electric field produced radially by stationary point charge is given by equation 10. The mobile test charge QO moves from point A to point B along the direction of the electric field E. The positive test charge moves farther away. The test charge experiences an electric force F given by Coulomb's law as shown here. We see that the force here is repulsive since both charges are positive. As the charge moves along the path, the force varies with radius r, which makes work not constant but varies with the displacement. To accommodate the changes of F, we express work as an integral function over the path r. Here the path taken has the same direction as the electric field, hence the derivative of its length is the derivative of its radial distance given as dr as shown in equation 14. Now we substitute the formula for the electric force to equation 14, and the angle between force and the displacement is 0, which results in a cosine value of 1. After manipulating the function we get the function for the work as shown by equation 15. Here we see that work function only considers the initial and final positions of the test charge, so it does not matter if the charge follows a curved path as shown by path A and path B. So the expression shows that the work done to migrate the test charge Q0 is path independent but only considers its initial and final state. Here we replace moving test charge by negative test charge while keeping the stationary point charge as positive. So we have two opposite point charges in space where you have a stationary point charge radiating an electric field. The negative mobile test charge moves away from the stationary point charge. The electric field produced will still remain the same, but the electric force is now an attractive force since they are of opposite charges and opposite attracts. The attractive force is then given by equation 16, and it points towards the positive stationary point charge. Now if we define the work done when charges have opposite directions, we rewrite the equation for work as shown here. So it goes the same for the calculation but with the key difference of the direction of the force and displacement r. So the cosine function of the angle will be 180 degrees, and we know that this will result in a negative value of work. Recall the expression for the work done for 2-point charges as shown by the equation here. Expanding this equation, we can get expressions for the individual electric potential energies at different positions A and B. We see that the electric potential energies are shown here, and we can write a general expression for electric potential due to 2-point charges as shown by equation 18. So we examine the change in electric potential energy as the test moves away from the stationary point charge. The change in potential energy here is done using the equation here. We see that the factor that determines if it is increasing or decreasing the difference of the ratio of the distances r. We see that the inverse difference of the distances r results in a negative value as the particle moves farther away from the stationary point charge. This decrease in the ratio of distances results also in the decrease in its electrical potential energy as it moves farther away. The change in electrical potential energy will give a negative value, so if we substitute this value, the work done will result in a positive value. Since the change in electric potential energy is decreasing, this means that its change in kinetic energy is increasing as it moves farther away from the stationary charge. So if the change in kinetic energy is increasing, then the test charge as it moves farther away must be accelerating. Here we have the same charge but moving towards the stationary charge. The change in electric potential energy as shown here. Examining the inverse distances, we see that it will result in a positive and in turn affects the change in electric potential energy as shown here. The change in electric potential energy is positive. Since the perimeter of the change in potential energy is positive, then the work done will be less than 0 or negative as shown here. Since the change in electric potential energy is increasing, this means that its change in kinetic energy is decreasing as it moves closer to the stationary charge. So if the change in kinetic energy is decreasing, then the test charge as it moves closer must be decelerating. Here we solve work using the force and displacement vectors. Using equation 2, we see that the displacement and force goes in the same direction, thus the angle between them is 0 degrees. This will result in a positive value of work. So the work done in moving the test charge from a similar charge that is stationary is a positive value. For this case where the charge moves in the opposite direction with the electric force. Using equation 2, we see that the displacement and force goes in the opposite direction, thus the angle between them is 180 degrees. This will result in a negative value of work. So the work done in moving the test charge closer to a similar charge that is stationary is negative. For this case, we replace the test charge with a negative test charge, which will have an opposite sign as the positive stationary point charge. The force direction will change and it now points towards the stationary point charge, and this force is now an attractive force. Now let us examine the change in electric potential energy. We see that it has a negative sign due to the negative electric charge of the point charge, and this affects the ratio of the displacement ratio, turning it to a positive value. This in turn affects the change in electric potential energy to positive as it moves away. So the work done will then be negative. Now let us examine the change in electric potential energy for the scenario where we have the negative test charge moving towards the positive test charge. The change in electric potential energy retains the extra negative sign due to the negative electric charge of the point charge. Since the ratio of the displacement will result in a positive, and if it is multiplied to the extra negative sign, the whole thing will result in a negative value. which in turn affects the change in electric potential energy to negative as it towards the positive stationary point charge. So the work done will then be positive. As the negative test charge moves away, it becomes less negative, thus an increase in its electric potential energy due to the inverse relation of the displacement and the negative sign. We see that the change in potential energy is positive as shown by the expression here. As the negative test charge moves closer, it will become more negative, thus a decrease in its electric potential energy due to the inverse relation of the displacement and the negative sign. Here the equation shows that relationship by the change in potential energy. For this case where the charge moves in the opposite direction with the electric force, using equation 2 we see that the displacement and force goes in the opposite direction, thus the angle between them is 180 degrees. This will result in a negative value of work. So the work done in moving the negative test charge farther from the opposite charge that is stationary is negative. Here we solve work using the force and displacement vectors. Using equation 2 we see that the displacement and force goes in the same direction, thus the angle between them is 0 degrees. This will result in a positive value of work. So the work done in moving the negative test charge towards an opposite charge that is stationary is a positive. General rule for a system having 2-point charges. The electric potential energy is positive if the two charges have the same sign. Otherwise, the electric potential energy is negative. Sample problem. A 3 nanocoulomb of charge Q is initially at rest at a distance of A equals 10 cm from a 5 nanocoulomb charge Q fixed at the origin. The Coulomb force accelerates the charge Q moves away from the stationary charge reaching a position B equals 15 cm. What is the change in potential energy of the two charge systems from point A to point B? To find the electric potential energy we use equation 15. The force between them will be repulsive due to like signs repel interaction. We recall that the work is equal to the negative change in electric potential energy U. After substitution of the parameters we determine that the change in electric potential energy is equal to a negative value. Here we have several charges that are stationary except for the test charge positioned at the center of them. The electric field experienced by the positive test charge Q0 is the sum of the individual electric fields generated by charges. This is given by equation 19. We can expand this further by writing it as a function of the individual charges and its relative displacements as shown in equation 20. So as the number of charges increases, the total electric field experienced by the test charge will increase also. We recall that for a pair of charges with varying displacement the work function is given by equation 14 and can be further expressed as equation 21. Now for multiple charge systems the work done is the sum of the work done by the individual charges. We can write a general equation that sums all this individual work done and it is written as equation 22. Now for the electric potential for a multi-charge system. We recall that for a pair of charges the electric potential energy is given by equation 18. We can express a function for multi-charge as simply the sum of the individual electric potential energies and it is written as equation 23. So if we add more charges we can just use equation 24, which is the general expression for measuring electric potential for several charges. We note that a single charge does not produce an electric potential and it needs at least two. Adding more charges that are assumed to be static will increase the total electric potential. Sample problem. Find the amount of work that must be done in assembling 4 charges of 2 microcoulomb, 3 microcoulomb, 4 microcoulomb, and 5 microcoulomb at the vertices of a square side with 1 cm, starting each from infinity. First we bring the first charge Q1 from infinity to the first vertex of the square. Since initially there is no charge initially, so the work done in moving the first charge is 0. Next we bring the second charge Q2 to the space which will interact with the first charge Q1 that is stationary. So the work done is 5.4 joules. We then bring the third charge Q3 in the space where there are charges already Q1 and Q3. These charges will interact with the third charge just like what happened with the previous charge Q2. So the work done in bringing the third charge is equal to about 15 joules. Finally, we bring the fourth charge Q3 to the space where 3 charges are placed already. So these charges will interact with the fourth charge. So the work done in moving the fourth charge is about 36 joules. Finally, the amount of work that must be done in assembling 4 charges is the sum of the work done by the individual charges, which sums to about 58 joules. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at @dieslearningstuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.